In this lecture, we will discuss a theorem which tells us that for any subspace U of vector space P, and V must be finite dimensional vector space. Okay, this is necessary. Then there exists a subspace W of P such that V is the direct sum of U and W. So this theorem tells us that जब भी हमें दो सबस्पेस U और V मिलेंगे, सॉरी, जब भी हमको एक सबस्पेस U मिलेगा ऐसा किसी वेक्टर स्पेस V का जो फाइनाइट डायमेंशनल हो, तो एक ऐसा सबस्पेस W एग्जिस्ट करेगा सच दैट दोनों का जो होगा डायरेक्ट सम वो V के इक्वल होगा. Okay, so we'll prove this. Okay, since V is finite dimensional vector space, since it is finite dimensional, so cardinality of basis will be finite. So assume okay, also since V is finite dimensional, U is a subspace of V, will imply U is finite dimensional. Okay, till here there should be no questions. Now since U is finite dimensional, means what? Cardinality of basis is finite. So okay, so now assume U1 U2 dot dot UM be a basis. Okay, this is a basis for U. Assume we have a basis for U. Since it is finite dimensional, we have a basis. Okay, so this is a basis for U, will imply U1 U2 dot dot UM is Li. This set is Li, means it is linearly independent, plus it will be also a spanning set for U. So since it is Li and U1 and UM are vector, these are the vectors from V. Since U is a subset of V, other way we can say that it is a vector subspace. So these elements will be in V also, and since it is in V and Li, so by extension theorem, this Li set can be extended to form a basis of V. Okay, so we will extend here U1 dot dot UM, and we will extend W1 to Wn, forms basis of V. Okay, we have a basis of U, and since this is Li in V, because U is a subset of V, so we can extend to form this basis of V. Now we got a basis of V. Okay, so now first we will show that U V equal to U plus W. Okay, and secondly we need to show U intersection W equal to only 0 vector. So first we will show this one, and we will show then after U intersection B equal to 0 vector. So okay, I erase these terms. Okay, Now to show this, what we need to show first that u plus w is contained in v. Okay, first is contained in, this content will be in v and v will be contained in u plus w, then equality will hold. Okay, so since u is a vector subspace of v, it will be imply u is contained in v, and w is also a vector subspace of v. Now actually w, we have w equal to a span of w1 dot dot wn. Okay, this is the w, and we need to show that v is the direct sum of u plus w. Okay, need to show v is direct sum of u, is direct sum of u and w. Okay, and w is the spanning set of w1 plus w dot dot wn. Okay, so here w is the span of w1 to wn. Okay, now since w is a subspace of v, will imply how it is a subspace, because this spans whole v, so it will be a span the subspace of v. This will span the subspace of v only. Okay, so what we can say here, w contained in v, and since both is a subspace, what this will imply, both is a subspace, then u plus w will contain in v. We know that addition of two subspace is also a subspace. Okay, I have proved in previous lecture. So first a statement, I have proved that u plus w is contained in v. Now we will show v contained in u plus w. Okay, so take any vector, let v belongs to capital V. So v, we can write the linear combination of a1 u1, because this is the subspace for v, this is the subspace of v, so we can write the linear combination of u1 plus a2, this is a u2 a m um plus b1 w1 plus dot 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 bn wn. So we can write v as the linear combination of u i's and w i's, but we know that this vector from here to here, this vector is in u. Okay, this is in u, because u1 u2 um is the basis for u, so this vector will be in u, and this vector will be in w, because w1 to wn is a basis for, is a spanning set, this will span w, so it will be element of w, so this will belong to u, this will belong into w, will imply v belonging to u plus w. Okay, because this belong into u plus w. Okay, so we have taken one element from v and shows that element is in u plus w. What does mean? This means that v is contained in u plus w. This will imply what? V equal to u plus w. Okay, because we have proved both the inclusion statement. Okay, v is uh, v is contained in u plus w, and w plus v, w plus u is contained in v. Okay, now what is need to prove? Secondly, that u intersection w should only contain zero vector. Then we can say that v is direct sum of u plus w. Okay, So let's assume, if possible, the if possible, assume assume a element an element V belongs to U intersection W. What does mean? Will imply V belongs to U and V belongs to W. So we can write V as a linear combination of A1 U1 plus dot dot AM UM. Okay, and this also can be written as V equal to B1 W1 plus dot dot B and Wn, because W is spanned by W1 to Wn. So this vector can also be linear combination of W1 to Wn, and U1 to Um is a basis for U. So any vector can be written as the linear combination of the basis element. But if we subtract from 1 and 2, so we get 0 vector here, b minus b equal to 0, and what we get here is a1 u1 plus dot dot am um minus b1 w1 plus dot dot, sorry, this will be minus minus, here it will be minus minus b and wn. Okay, this is it. But what we know that the u1 to um and w1 to wn is a basis for v, and say all the coefficient will be 0, means a1 equal to 0 equal to am, these elements equal to 0, and b1 equal to 0 equal to dot dot bn. So what does it imply? That v is the linear combination of u1 u2 m and their coefficient is 0. It means this vector is 0 vector. So we prove that the vector, and say u intersection w equal to only 0 vector. So what we proved, that v is the direct sum of u plus w. Okay, we have proved.